That was Amy McDonald singing No Roots. Now, the next thing that I want to talk about in this conversation of ecosystems and restoration ecology is how energy is transferred from one organism to another. So I keep mentioning how we have these different types of consumers and producers and how different things are doing different activities with energy and with nutrients. And all of these things, of course, are joined in the ecosystem because they are transferring energy from one to another. So primary consumers, the herbivores, they can only eat a small portion of autotrophs. So you know you've got a whole lot of trees and grasses and all sorts of plants in an ecosystem. And you don't have so many insects and so many cows and deer and other grazers going in and eating, you know, all of these plant materials. There's only so much that these animals can do. And so you have a whole lot of stuff that's left over for the tritivores to consume. And these guys, again, they're going to eat these things once they are no longer growing. So when a plant has reached the end of its life and then it dies, it's just going to kind of wilt and stay there until the decomposers come along and eat up all of that material and turn it into something that can be accessed by another organism. Now, primary consumers are going to then use some of that energy for themselves, the energy that they make, that they get from photosynthesis. They are going to use some of that for themselves, but most of it is going to be excreted into the environment, and this also is going to be something that the detritivores can consume. And when I say that they're using some of the energy for themselves, what I mean is they're going to be metabolizing their own food, they're going to be generating their body heat, they're going to be doing the kind of basic life support processes that they need to do to keep themselves alive, and then all the rest of that energy is going to be available for other things. So the secondary consumers are only getting a fraction of this original energy, as I said, and then again you've got tertiary consumers, so the carnivores and the carnivores of the carnivores, that are getting a fraction of a fraction. And so that means that you actually end up losing quite a lot of energy at each of these steps, because you've got things using it for themselves, you've got them releasing it via heat into the environment, you've got them excreting things that are going to only be used by the decomposers, and so you end up having a narrowing, basically, of energy as you go further and further along the food web or the food chain, however you want to think about it. Now, birds and mammals are actually particularly bad in terms of passing on energy, because we work really hard to maintain our body temperature. It's quite important for us to have a certain amount of heat in order to keep ourselves safe and healthy, and so we use a whole lot of energy for that process, and that means we don't have as much energy to give to the animals that might consume us. Fish are slightly better at this, and insects and microorganisms are the most efficient, and they're the things that pass on a lot of energy to the next step. And that's actually why you have people in lots of places in the world who will eat insects, because insects are, no matter how gross you might find them, whenever you have a dinner plate in front of you full of these things, they are actually quite good for you in terms of energy content. Now, each of these consumer groups that I've mentioned is a different trophic level. And so you can look at the flow of energy by measuring trophic efficiency. And this is the efficiency throughout that whole movement from one trophic level to another. And basically, you generally only have about 5 to 20% of all energy from one level being passed on to the next, because of all these things I mentioned earlier that cause it to be lost at each stage. And the amount of energy that winds up at the end of the line is what determines how many top-level carnivores, things like lions and sharks and wolves, an ecosystem can support. And so usually we only have about 0.1% of all chemical energy fixed by photosynthesis finding its way to a tertiary consumer. And that's obviously quite a small number, and that's why most food webs only have 4 or 5 trophic levels, and that's why you often don't find that many top-level carnivores in terms of one species, or lots of different species in the same place. You have to have a really fantastic and diverse and abundant and productive ecosystem to have multiple trophic levels and multiple carnivores at the end of that line. And actually, one of the things that's kind of interesting about this concept is bringing it back to humans. If we were more aware of these kind of things and choosing our own diets, we could actually use our space a lot more efficiently than we do. So, for example, it's actually quite a bit better for us in terms of energy to to eat soybeans directly, rather than to take those same soybeans and give them to cows and then use those cows for our own meat. And now, obviously, it's not going to be quite the same having a bowl of soybeans and having a plate full of steak in terms of, satisfying your taste buds or satisfying a certain feeling in your stomach when you're really full from eating meat. But this is the kind of thing we might have to think about in terms of trade-offs as the human population grows and we're taking up more space and we're needing more resources. And so if we want to try to balance these things out a little bit, we might want to say maybe, a certain number of days of the week we're going to be eating vegetarian instead of eating meat, because this does preserve energy a bit better and allow us to get more out of the space that we've got. So where do all of these nutrients that I'm talking about come from to begin with? And this is actually a question that kind of takes us back around to the story of the wilds, because remember I said that it was depleted, it was a really poor area because all of these nutrients had been taken away. And so you do have to think then, well, if nutrients can be taken away, they can be put back in, and where is it in a natural setting that they're coming to begin with? Well, basically you've got minerals that are in the soil already from previous organisms in most places, obviously not the wilds, because as I said, the topsoil was taken out. But you do have minerals in the soil, and these guys are really important because they can cycle into and out of ecosystems, because you've got these primary producers that are able to pull them up out of the soil, and once they're in the primary producers, then you can have them available to the herbivores and the carnivores, etc. And when these minerals are depleted, then they need to be restocked. And this happens naturally in biogeochemical cycles. And these are nutrient cycles that include both biotic and abiotic components. And these can happen on both local and global scales. So locally, you've got the movement of chemicals that are usually a bit heavier, and so they're found in the soil and the water. And these are things like phosphorus and potassium and calcium. And that's how these things are moved from one place to another. You've got the movement of soil, you've got the movement of water, you've got these organisms that pull them up out of the ground and pass them on to other organisms that can then move across a certain amount of space and carry them elsewhere. Then you've got your global cycles, and these are things that generally have to do with the movement of gases from the atmosphere, so light things that are up above everything else. And by light, of course, I mean weight, not photosynthetic light. And these are things like carbon and oxygen and sulfur and nitrogen. And basically all of these things can be found in different types of what we call nutrient reservoirs. So sources that store these in some format or another so that it's either accessible or not accessible depending on what kind of reservoir it is. So basically there are 4 different types of these things, and they can be defined according to whether they contain organic or inorganic molecules and whether the materials are either directly or indirectly available for use. And I'll kind of expand on this a little bit. So the first of these reservoirs is something that contains organic materials that are directly available as nutrients. And so this is what you and I might colloquially refer to as wildlife. So all plants and animals and fungi, etc. We're all made up of organic molecules, materials, and these things can be eaten automatically. If you've got a carnivore that comes along, it can eat any of these herbivores and get nutrients. If you've got a herbivore that comes along, it can eat any of these plants and get nutrients. So they're readily available. The next type of reservoir is one that contains organic materials that are not available. So when you know that whenever we die, whether animals die, whenever plants die, often these things are not immediately taken up by other decomposers, and so they'll just kind of sit around for a while and they'll start to fossilize. And we know of these things as fossil fuels. They become peat and coal and oil, and all of these things, as I said, have been made by fossilization of the items from category 1. And fossil fuels can be burned, and then this releases these inorganic materials so that they're again available for use. But until they are burned, they aren't available, and that's why they're a slightly different category than that first reservoir. Now the third category, actually before I go to the third category, I should mention that fossil fuels can also be created by processes of respiration and decomposition and excretion of these things in category 1. So there are lots of different ways that we can have these things being stored and being accessed. So inorganic materials can also be available or unavailable as nutrients. And these are things that can be made available once again by things like weathering and erosion. So inorganic materials are going to be these things that basically are compacted and turned into rocks. And so once you've got a lot of wind that goes past or a lot of water that comes past, it's going to take all these inorganic materials and break them down into little bits, and those little bits are going to go into areas where these primary producers can access them and turn them into things that the rest of us are able to use. And of course, then you also have inorganic materials that are available as nutrients, and these are the things that I've mentioned earlier that you've got already in the soil, that these things like the mycorrhizae and the root bacteria can access and give to plants. So the things that go through these sorts of processes include water and carbon and nitrogen and phosphorus, and all these guys have cycles and they all involve reservoirs, and different cycles are more or less complex. So the water cycle, for instance, is pretty easy. Just to give you an example, we know if it's a cycle, there's obviously no start or end, but I'll just kind of choose precipitation as a nice place to start. So if you imagine precipitation that's occurring over land, when the rain falls, it's going to percolate through the soil, and it's either going to evapotranspirate back into the clouds, or it's going to go into the ocean eventually via runoff and groundwater. Once it's in the ocean, it can either evaporate into the clouds that are over the water and then precipitate, and if it precipitates, it can then go back into the ocean, or it can be moved by wind over land and then start the whole process all over again. So that's relatively brief. There are only a few steps. They're only linked by so many different arrows, and so that's nice and easy to remember. But some of the other cycles involve many more steps and are much more complex. And this is particularly true of the nitrogen cycle, for example, because nitrogen goes through lots of different intermediate steps and different compounds that are produced and uptaken by a lot of different organisms. And so these complex nutrient cycles can actually be disrupted quite easily. They're very sensitive because you do have all of these organisms that together have to contribute to getting these things cycling through the environment from one organism to another. That was Brooke Fraser singing Something in the Water. Now, right before the break, I was talking about the different types of nutrient reservoirs, and I was talking about how things cycle through ecosystems and within ecosystems. And there's quite a lot of information that we know. I've obviously distilled this down for what I'm talking about today, but the reason that we know about all of these cycles in the detail that we do, well, one of the reasons I should say, is that we've used isotopes, which are variants of chemical elements that have different numbers of neutrons. And if you look at certain places, we know that there are tendencies of these places to aggregate certain types of isotope and certain amounts of isotope. And so we know, for example, that places that are very far north have kind of different isotope conglomerations than areas that are down at the equator or even further south. And so we can kind of see where these chemicals are starting off and where they end up, and we can also see them within an ecosystem and where they move from one organism to another at a different trophic level. And so both locally and globally, we can watch these movements of isotopes in order to understand what are these compounds that are quite important, how long do they take to go through, at what point do they go through, where are they starting off and where are they ending up, and what are the amounts that are used within an ecosystem. And it can allow us to get quite a lot of information. Now, the rates of cycling are driven primarily by the speed with which detritivores can decompose organic materials. And this in turn is controlled by things like temperature and moisture and nutrient availability. So things like basically the environmental conditions are impacting what the decomposers can do. And again, as with primary productivity, we know that warmth is positively associated with speed. And so when you've got things like cold and dry areas, or cold and wet areas like peat bogs, you then have a whole lot of stuff that's, really nice nutrients that are all sitting around just waiting to be used. It's really the nice warm places where these nutrients are cycling through quite quickly. And plants, on the other hand, are the main organisms responsible for retaining nutrients in an ecosystem. So you especially have a lot of retention in areas where you have plants that grow enormous, and so they have lots of nutrients shunted through different parts of their body, and also when they live for quite a long time, because once they've uptaken those nutrients, they may hold on to them through their lifespan, and they're not returned to the system until decomposers have a chance to get in there and take all the little bits apart. So once plants are removed, and especially when plants and chemicals both are removed, then you've got a huge disruption of cycling. And this means that you've got this point where ecological successions can take over and allow ecosystems to recover naturally from disturbances, or at some point you might have this all stopped because too much has been taken out and nothing is going to happen unless we humans go in and try to make a difference. And this is what brings us back around to restoration ecology. So what does restoration ecology do? Well, as I mentioned earlier at the beginning of the show, it allows us to initiate or speed up the recovery of a degraded system. And I should mention that even though we do have this lovely thing called ecological succession, where you've got certain plants and founding species that will come in and make the chemicals and the nutrients available to other species that will then bring them in and allow things to develop back into what a system once was, it's not always guaranteed that it will look exactly the way that it used to, or that it will function exactly the way that it used to. It will rebound in some way, but it might not ever be exactly what it was before. And this is also the case when humans step in. You never know whether it's actually going to be exactly the same, but we certainly can make every effort to have it work as well as it used to. So restoration ecologists look to see what's preventing a system from returning to its earlier state, and then they try to supply that missing ingredient. And one of the things they might first have to do is address the physical structure of an ecosystem. So people might go in, and let's again take for example mining. They might end up changing the course of flowing water, they might alter the topography, and so you have to go in and make sure that the land is shaped in the same way that it once was, or at least to shape it in a way that's conducive to introducing nutrients and chemicals and having those stay in the area rather than leach back out and flow out of the ecosystem into another. Ecologists also do something called bioremediation, and this is a process of using organisms, often prokaryotes or fungi or plants, so the primary producers, to detoxify polluted ecosystems. And this takes advantage of the fact that we do have lots of organisms that are specially adapted to accumulate high concentrations of potentially toxic metals in their tissues. And these are things like zinc and nickel and lead and cadmium. So if you introduce these species and let them take all of these things up into their tissues, you can then go in and harvest them and carry away the metals when you carry away their tissues, and you can just get it out of the ecosystem. For example, there's one species of lichen that can be used to get rid of uranium dust that's left over from mining. And another example also is these prokaryotic species that metabolize elements from soluble forms that can be washed around in water to insoluble forms that are less likely to leach away into streams and groundwater and then pollute neighboring ecosystems and also cause problems for we humans. Now, something else that ecologists are interested in is biological augmentation, and that's using organisms to add essential materials to a degraded system. And first you have to go in and determine what's been lost and see what's limiting the recovery, and then target these things. So you want to encourage the growth of plants, for instance, that are thriving in nutrient-poor soils. That are thriving in nutrient-poor soil. So we have lots of things that are known to be nitrogen fixers. And these are things like legumes, peas, peanuts, red buds, all these sorts of vetch is a great example, clover, things that will grow kind of in wasteland areas along the road. The reason that they do that is because these are nutrient-poor areas, but they don't mind that. They're able to take lots of stuff out of the soil and convert it into something useful. And so we want to introduce these kinds of colonizers that can go in and make it easy for other animals and plants to then come into the ecosystem and have access to those materials. And also this includes things like mycorrhizae that you might want to introduce in order to help plants meet their nutritional needs. Now, animals might be reluctant to recolonize on their own, and they may also not remember or know how to find the area. As I mentioned last week, when I was talking about how certain populations have memory of how to migrate appropriately, how to get to the right place, what time to leave to get there, that sort of thing. You might have animals that no longer remember exactly what this habitat is, whether they should go there and use it, or they might have had a bad experience there because of the disruption, and so they don't want to go back. So you might have to encourage them. And to do that, you might do things like introducing a burrow or a perch or a nest box, and basically just make the habitat more attractive and try to encourage them to come back. Now, the idea of restoration ecology also encompasses the creation of entirely new sites, and these can replace others that have been destroyed and either will not or cannot be reclaimed. So in the US, for example, we have a law where if you build in a wetland habitat, you have to then create a new wetland to replace it. So when we have things like Walmarts that are put up and they have their parking lot that maybe is in a kind of a wetlandy area, often you will find that they create then another new wetland off to the side with lots of cattails and ducks and frogs they're trying to bring in. And there's a lot of argument about whether these techniques are actually as efficient as we would like them to be, and whether they're actually creating the sort of thing we want. So I mentioned this example of the Walmarts and the cattails and whatnot, because this is actually something that's been quite extensively studied, because wetlands in particular are a real issue around the world because they do have so many ecosystem functions and they do help us in so many ways. And this is a habitat that we are often targeting in order to build new things. And so there's a real concern that whenever we go in and try to kind of recreate these or restore them in some way, that we're not really getting back what it was that we've already lost. And so often you find people argue that all these restoration ecology efforts are making the habitat maybe look similar to the way it used to look, but then not have quite the same ecological function. And that might be because it's no longer as complex as it once was, so maybe there are fewer trophic levels or less biodiversity, but also there might simply be a matter of time. And so it takes a long time to get all these organisms back in place and to get all these relationships set back up and all the nutrients and chemicals put back into the environment. And so maybe we just don't have time to see the positive effects of these efforts. And we do know, for example, that grassland habitats are maybe a bit easier to restore than forest habitats. And artificial reefs, we know, can be quite successful. So it all kind of depends on what organisms were there to begin with, how many of them there were, how complex was the trophic interactions, and that sort of thing. So clearly one of the big challenges that restoration ecologists face is improving their techniques so that they can make sure that their ecology actions are working faster and they're working more efficiently, they're targeting more species simultaneously, and also so that they can make restored areas more similar to both their previous form and their previous function. And on that note, I think I will end up today with Coldplay singing Fix You.